So we've discussed boiling point here and there previously in the IMF's video, and it may have come up whenever I was discussing vapor pressure. So we're actually going to dig deeper into it and look at kind of what's happening at the molecular level and also how it relates to vapor pressure. So I want you to visualize and actually have this picture here, luckily, for us to visualize when something is being heated up, for example, water. You will have like bubbles, right? Pockets of what seems to be like air starting to pop up in the liquid. Now, what is going on there? The heat applied is heating the molecules up enough so that they turn into vapor. So there's pockets of vapor inside that liquid. That's why you start to see that boiling. That's what boiling is. And this occurs at a certain temperature. That's the boiling point. And it depends on the pressure above it. So whenever the vapor pressure of a liquid increases enough, right, because this is an open container and the vapor pressure will keep increasing. It's not going to stay constant the way that a closed container will occur. The vapor pressure will keep increasing until it is equal to the external pressure above it, atmospheric pressure above it. And this, whenever these two equal the same, the vapor pressure of the liquid and the external atmospheric pressure, that is whenever the liquid reaches the boiling point. Okay, so two things about vapor pressure and boiling point. So there is something called the normal boiling point. This is just a kind of like something standard so that we can easily compare different boiling points of different liquids. So the normal boiling point is the temperature at which the vapor pressure of the liquid will equal 1 atmosphere. So 1 atmosphere is also equal to 101 kilopascal. That's why we have kilopascal right here. But anyway, at 101, which is this dashed line right here, which I'm gonna write over, these you can see the boiling points of all of these different liquids: ethyl ether, ethyl alcohol, water, ethylene glycol. So this is just to compare and have kind of like a standard number that we can use. Now, second thing of this slide is that second major takeaway is that the lower the external pressure, the lower the boiling point of the liquid. So to illustrate this, I want to show you a list of different elevations. So we have Mount Everest, a whole bunch of different mountains. Mount Everest is the highest, obviously. But these different elevations, you can see that there is a different atmospheric pressure associated with them. So the higher the elevation, the lower the pressure. The lower the elevation, the higher the pressure. Now look at what this does to boiling point. So at the lowest atmospheric pressure, we have a boiling point for water of 78 degrees C. Now we know that the standard boiling point of water is 100 degrees C. So what's happening here? So at 1 atmosphere is whenever we have this specific boiling point. So boiling point depends on the pressure of the atmosphere surrounding the liquid. So at 1 atmosphere, right, in Boston, Massachusetts, sea level, the boiling point of water is 100 degrees. But as you increase the elevation, so decrease the atmospheric pressure, you will see a lower boiling point. So in this example, we will be looking at boiling points at a reduced pressure. So again, just to remind you, this chapter is very conceptual. It's more about you being able to apply concepts and reason with them. So here we have a typical atmospheric pressure in Leadville, Colorado, where the elevation is about 10,000 feet, is 68 kilopascals. Use this graph to determine the boiling point of water at this elevation. So 68 kilopascals. Where is that on one of these axes? We know that kilopascals is right here. So let's look for, or let's estimate around where 68 is. So we have 53 and 80. So in between that is what? There's about 30 in between that. So let's say plus 15, 53, that's 68. So that's exactly. So around halfway, that would be, those would be our boiling points at this elevation, right? So whatever the pressure is, and in this case it's 68 kilopascal, we have to find the boiling point of water. So we're looking at water, we're looking at this blue line right there. We need to find wherever it intersects, and it happens to be right there. Now we're going to trace back to what the temperature is, and it's pretty much between 80 and 100. Sorry, I wrote over it. So that would mean that the boiling point, the temperature, would be 90 degrees C. So I would estimate this to be 90 degrees C. So because this is lower than, sea level, this is a lower atmospheric pressure than sea level, we are going to see a lower boiling point because there is a lower pressure. So there is an equation called the Clapeyron equation. This equation is useful because you can use just two measurements of vapor pressure and temperature to determine, any other unknown, right? And it also ties the enthalpy of vaporization into the equation. So although it's useful because you can essentially get whatever unknown you have if you have everything else that's known, it is limited by the fact that it gives less precise results, and it's also limited by how many data points you have. Now, I am not going to make you calculate anything with this equation. This isn't physical chemistry. I consider this like higher, like a higher course level chemistry work. But I do want you to know that it exists. So we've been talking about vaporization and how, whenever a liquid reaches a certain temperature, the boiling point, it'll vaporize away. But we haven't talked about how that requires energy, right? We saw how heat is required in order to boil something away. And that is actually, that has to do with enthalpy. So vaporization is an endothermic process, so it requires heat. So think about how you put that little kettle or pot over the stove, and you're putting heat into it to boil it away. So it's endothermic. Specifically, we refer to how much energy is required as the enthalpy of vaporization. Now, to illustrate how something can be exothermic, how vaporization can be, endothermic, is whenever you are sweating, right? So for example, Miss Puff, she's sweating right there. I relate to that. The reason that you feel cooler and the reason you're supposed to leave sweat on your skin, you're not supposed to wipe it away, is because your body's trying to cool down. And the way that it cools down is that the water evaporates away, and it requires heat for it to happen. The heat that is used for that to happen, for the water to evaporate away, is the heat from your skin itself, right? You had some physical activity, your body is heating up. To compensate that and cool itself down, it's gonna sweat, and then it like pulls an Uno reverse card and it uses that same heat to evaporate away, and then you end up being cooled down because that heat is gone now. So whenever water is going from a liquid to a gas, so it starts off as a liquid like sweat on your skin, and then it goes into a gas, it requires plus 44 kilojoules per mole. And then the converse is true. So whenever something is going from gas to a liquid, so it's condensing, it's going to be the opposite. It's going to release negative 44 kilojoules per mole. So here we have this relationship where they are equal to each other, but they are opposite sign. And just to clarify, this VAP right here means vaporization, and that CON means condensation. So just to make sure everybody's on the same page. So we have finally reached a problem in this chapter that requires some math. Now we are going to be using the enthalpy of vaporization to determine how much energy we need to evaporate a certain volume. So we are going to use something called dimensional analysis. So we learned about that in Chem 1. And you're probably thinking, ma'am, I took that a year ago. I took that 6 months ago when COVID started. I have no clue how to do that anymore. It's okay. Just use this problem as an example. And from there, trust me, it'll come back after you maybe practice one on your own. So let's do this one together and then you will be set. So we are starting off with 1.5 liters of water and we're looking for how much heat is required to evaporate that. So we have this temperature, we have this heat of vaporization that tells us that it requires 43.46 kilojoules per mole at 37 degrees to evaporate 1 mole of water. So we need to find a plan, right? Because our known is 1.5 liters and our unknown is how much heat, right? So we need to devise a plan first of how to convert this, and then we can go from there. So we have liters. We're starting off with liters. What can we possibly tie this to next? So if you don't know this already, anytime you have something related to moles, your goal, your first instinct should be to somehow get to moles. That should be your very first instinct anytime you have moles of something. So we're starting off with liters. We want to get to moles. In order to do that, we actually have to convert this using the density of water to grams. So we are going to use the density. So I'm just going to write D for density to get to grams or mass, whichever one. From there, we can actually use the molar mass to get to moles. Once you're at moles, you're in a good spot. From there, we will use the heat of vaporization to get to just joules, so heat, right? And that's our plan. So let's go ahead and set that up. So we're starting off with 1.5 liters. So the density of water is 1 gram per 1 ml. We can scale up and we can make this 1,000 ml, so a liter, and 1,000 grams. So we can say 1 kilogram is also 1 liter. So these are all conversion factors. So don't be scared about these. These are just some simple conversion factors. So we're going to set that up. 1 liter is 1 kilogram. And then let's just get to grams. So there's kind of an extra little step in there. So in 1 kilogram, there is 1,000 grams. So sorry about that. I didn't include that in the plan, but here we are. And then the molar mass. So the molar mass of water is 18 grams per mole. So molar mass, if you don't remember how to do that, we are taking the formula and we are adding the masses of all of them. So for oxygen, it's 16 grams per mole. Sorry, that's a mole. And then we have 2 hydrogens, that's 2 grams per mole total. So total, this adds up to 18 grams per mole. So I'm going fast just because this is Chem 1 stuff. So 18 grams of water is 1 mole of water. And then from there, we just add in the heat of vaporization. So mole is going to go at the bottom. We want that to cancel out. And our 43.46 kilojoules goes at the top. So moles cancels out, grams cancel out, kilograms, liters. And from here, you should end up getting 3.6 times 10 to the third kilojoules. So if you have any questions on calculating this out, or just typing it into your calculator and how we got this answer that has scientific notation, just let me know and I can help clear that up for you. So next we're going to talk about melting and freezing. So far we've talked about vaporization, and now we're talking about vaporization and condensation, right? Because those go the same way. They go from gas to liquid or liquid to gas. In this case, we are going from solid to liquid, liquid to solid, right? That's what melting and freezing both do. They transfer between those two. So as the solid is heated, its temperature rises and the molecules will begin to vibrate more vigorously. As they vibrate, they will reach something called the melting point if you're going from solid to liquid. At this point, the molecules have enough energy to overcome the IMFs that hold them together, right? And this causes them to turn into a liquid instead. So same idea how we had enthalpy of vaporization, we have enthalpy of fusion. So this, think about how whenever something is fusing together, it's becoming, more compact. So think of how we go from a liquid to a solid. It's going from flowing freely to becoming a solid where things don't flow the same way. So you have heats associated with them, or enthalpies associated with them. So if you go from solid to liquid, you will have a positive enthalpy of fusion. It requires heat in order for that to happen. Whenever you go from liquid to solid, you release heat. And again, they are the opposite. So fusion, solid to liquid; freezing, liquid to solid. So next we have sublimation and deposition. So these are kind of the weird ones. So I like to say, or I like to think they're like an outcast, because everything else, freezing, melting, you see that in person. You see ice melting, you see ice or water freezing. For condensation and vaporization, you see water condensing on the outside of your glass or can of soda. And for vaporization, you see water boiling away whenever you're cooking something. So you see these things in our everyday life. But for sublimation and deposition, you don't see it. So it's kind of hard to imagine, but they also have the same types of heats associated with them. So heat associated with sublimation will require heat, so going from solid to a gas, versus deposition is going from vapor to a solid. You will release heat. Here we have iodine that is in a tube, right? And it's subliming, so it starts off as a solid at the bottom. As it starts subliming, it produces a purple gas as it reaches a colder part of that tube up here at the top. So it's rare, but as you can see, it does occur. So we actually have heating and cooling curves. So for example, with water, let's say we wanted to go on the journey with it from it starting off as ice, as a solid, all the way to vapor. So we could actually look at and measure all of the heat necessary for all of this to happen. So first you would start off as a solid or ice, right? And then it would require a certain amount of heat in order for it to melt. As it melts, it can stay at that heat until it all completely finishes melting. At that point, when it's all completely melted, you would require a large amount of heat added, which is this amount of heat right here. At that point, it would be at this entire point in the curve, it would be water, right? So if you keep putting heat on it, eventually it's going to boil. So at 100 degrees, let's say we're at 1 atmosphere pressure, 100 degrees, it will start boiling away. So again, it's going to lag because it's going to take a while for everything to boil away. And then finally, when it reaches the point where everything boils away, everything becomes a vapor. So there is something called a phase diagram. So phase diagrams have kind of special terms associated with them. So first let's go over those. So the regions are states. So just like on a map where you have different regions, here we have different regions and they're color coded. So this brown is a gas, this purple is a solid, and this more pinkish purple is a liquid. The lines represent state changes. So at this line is wherever you will, let's say you cross over here to the top, you will reach liquid. You will enter into a liquid phase. If we cross over here into the brown, you will reach gas phase. So whenever you have everything cross and intersect, you have something called the triple point. So although this is weird and it's very hard to imagine, you can have all three states exist at once. I know it's weird, but it can happen at a certain temperature and a certain pressure. So the point of these phase diagrams is that you can map at different temperatures and different pressures, and you can predict when and what a substance will be in terms of its state. So like I said, phase diagrams can be useful because we can use them to determine at what temperature, what pressure something will be, what state it'll be in. So for example, water, the way that dry freezing works is that we preserve these foods that have a very high water contact by placing them in a vacuum with a pressure. So in a vacuum means they like suck out all the air, and then they have a pressure of less than 0.2 kilopascal. So it's very, very low pressure. At this pressure is actually when ice sublimes. So we can use these phase diagrams to determine things that are useful to us, like this in real life. So now we're going to determine the state of water using a phase diagram, specifically water's phase diagram, to determine the state that it'll be at certain temperatures and pressures. So I'm actually just going to do B because these actually are pretty similar to each other. So let's look at 25 degrees C and 90 kilopascals. So at 25 degrees C, so here is 0 and here is 100. So I would say a fourth is maybe right here. And then 90 degrees C, so here we have, 90 kilopascals. Here we have 100, so I would say maybe, right there. You're just going to see where the two meet, and that is how you use phase diagrams. So we can see that these specifically here meet in the water area. So that means at this temperature and at this pressure, it would be water. And you can do the same with any temperature or any pressure given. So to finish off talking about phase diagrams, we're going to talk about supercritical fluids. These are also something very strange. You don't need to know more than what I have on this slide. So if you ever take something called physical chemistry, it's the worst chem ever. You will learn more about this entire section of this chapter. But anyway, supercritical fluids have properties of both gas and liquid states. So the temperature required to reach that is critical temp, pressure required to reach that is critical pressure. So at this critical temp, the gas cannot be condensed to a liquid no matter how high the pressure gets. So imagine you put a bunch of pressure and you're expecting it, okay, I'm pushing all of these molecules together. That's what pressure is. I would expect them to condense and eventually, give in to the fact that there's so much pressure. But because we have this very special temperature called the critical temp, no matter how high that pressure gets when you reach that critical temp, it will not condense into that liquid. So here you can see we're increasing the temperature. First we have the liquid and the gas. Makes sense, right? So this is like looking into let's say a glass of water where the water is at the bottom and then the gas is at the top. That's what you're looking at. As you're increasing the temperature, we find that we end up having something called the supercritical fluid, which we just discussed. But it's like one state. So again, very weird, very strange, but that's about as much you need to know about this.